Welcome to the Organic Chemistry video content to accompany the Organic Chemistry 1 lecture guide and the Organic Chemistry 1 primer. The problems in this video homework come from Part 3, dealing with the reactions of alkenes, alkynes, and radicals. Our first task is to provide IUPAC names for these alkenes. We begin by numbering our parent chain such that the double bond is closest to one end. In this case, the closest we can get it to the end of the parent chain is starting the double bond at position 2. And the parent chain's total length is 7, so this is some type of 2-heptene. Next, we identify any substituents coming off of this parent chain, and we see a methyl group at position 3, so we'll add that to the name as well. The last thing we need to do is put in a label of configuration. To do that, we consider each of the two carbons in the double bond separately. We see that we have a high priority substituent here compared to the hydrogen that's not drawn. And on the other carbon, the higher priority substituent is this longer chain compared to this methyl group. So when we consider the high priority substituents, they are on opposite sides of the line that bisects that carbon-carbon double bond along the carbon-carbon double bond axis. This is an example of an E isomer. So the complete name is E-3-methyl-2-heptene. In that case, you number the parent chain such that the alcohol is as close to the end as possible. Here the OH can be placed on carbon 1. So this is some type of hexene-ol. And specifically, this is a 4-hexene 1-ol, where the numbers 4 and 1 tell us where the alkene and alcohol units are, respectively. We also have two methyl groups at position 3, so we need to add the term 3,3-dimethyl in front of the rest of the parent chain composition. Finally, we need to assign an E or Z isomer designator in front of the name. The two high priority substituents coming off of the carbons in the double bond are the methyl group on this side and the whole rest of the chain on this side. Those again are pointed in opposite directions coming off of the carbon chain. So this has the complete name E-3,3-dimethyl-4-hexene-1-ol. In the next example, we number the chain again to position the alkene as close to the end of the chain as possible. Here it starts at position 2, and the parent chain's length is 6. So this is some type of 2-hexene. In terms of substituents, we have methyl substituents at positions 3 and 5. So in front of the parent chain, we need to put a 3,5-dimethyl. Finally, we need to assign a designator configuration. If we look at this carbon, the higher priority substituent is this methyl group compared to this hydrogen here. If we look at the top carbon, this double bond, we have a methyl versus this longer piece of chain. This longer part of the chain will win out, and we see that we have both of the higher priority substituents coming off of the same side of that carbon-carbon double bond. So this is an example of a Z isomer. So the complete name is Z-3,5-dimethyl-2-hexene. In our final example on this page, we see that we have both an alcohol and an alkene unit in the same molecule. So we again number this chain so that the alcohol is closest to the end as possible. So it's at position 2 along this chain. So the base structure we will use is that this is some type of 4-hexene 2-ol. We'll put that in. We also have a methyl substituent at position 4. So this is an example of a 4-methyl 4-hexene 2-ol. This example is different from our other examples in that we have a chiral center, which is an R configuration. We also have this double bond, which very much like the one above it, is in the Z configuration. The rule is that you put the E or Z label in front of the label for the configuration of the stereocenter. So the full complete name is Z-R-4-methyl-4-hexene-2-ol. In addition to being able to name alkenes, we are going to be doing reactions on alkenes, and we'll need to be able to assess the relative stability of alkenes. As discussed in the primer, the heat of hydrogenation is a quantitative way to measure the stability of alkenes. The less stable an alkene is, the higher the amount of heat released upon hydrogenation will be. And in this example, we're asked to rank these. Now, the first thing we look for is the number of substituents that are not hydrogen, the number of carbons that are directly attached to the doubly bound carbons in these structures. We have 4 carbons attached to the carbon-carbon double bond carbons in this case. Only 2 in this case, 2 in this case, 3 in this case. One of them is a hydrogen, it's not drawn, and only 1 in the case of the far right structure, where the other 3 are hydrogens. So the most heat will be released by the monosubstituted alkene. What happens when we have a tie where both of these 2 alkenes have 2 substituents? They're both disubstituted, but one is trans and one is cis. Well, due to the steric repulsion of these proximal groups in the cis isomer, it will release more heat upon hydrogenation. The trans alkene will then rank 3rd in terms of the heat released. 4th will be the tri-substituted alkene, and the least heat will be released from the most stable, already tetrasubstituted alkene. Now that we have in place a framework by which we can name alkenes and assess their relative stabilities, we can start to learn some of the specific reactions and look at reaction products. The first reaction that is covered in the primer and the lecture guide is the hydrogenation of alkenes. And these hydrogenation reactions are mediated by the reaction of either palladium or platinum catalysts with hydrogen gas. And sometimes people use deuterium instead of hydrogen, where D is just a heavier isotope of hydrogen called deuterium. As with all of the addition reactions to alkenes that we will see, we really need to know what things add to the alkene double bond. In this case, a hydrogen adds to each side, and how they add. In this case, the 2 H's that add will add syn to one another. This is especially important in cases like this first one, where we have a cyclic starting material. If the 2 H's that have added are syn to one another, then the 2 methyl groups that were already present in the starting material must be pointed the opposite way of the added hydrogens. This compound also is symmetric, so we do not get multiple distinct isomers. We have one achiral product possible here. This second example shows the use of deuterium. Deuterium will add to the same side, syn addition, in the same manner as hydrogen would add. This again generates a molecule that is symmetric, yet has chiral centers. So both of these compounds are mesocompounds, and we get one single achiral molecule as the product. But it's not always the case that we get a meso product as the product of this hydrogenation reaction. Let's consider this third example. If we look at this, 2 hydrogens can add from one phase. If they come from the top of this molecule, if we consider the top above the screen and the bottom below the screen, we could have these 2 hydrogens add to the same side. We have the ethyl group right here on the same side as the methyl group. The other ethyl group will be away from us. That's this one. And then a methyl group will be away from us on this side. The other possibility would be that the 2 hydrogens would come from behind the screen, pushing this methyl group up. The ethyl group would then be up. This ethyl group in the front would also be up. And then we have a methyl group that would be up and away from us. These are 2 distinct isomers because there are chiral centers and there is no plane of symmetry in this molecule. You would have to draw both of these isomers in order to meet the criteria of the question asking you to draw all distinct isomers produced as major products. You'd expect a 50-50 mixture of these, and this would be a racemic mixture. Now the reaction we just did utilized the E isomer. If we consider the same hydrogenation of the Z isomer of this molecule, we'll get a different outcome. If we try to add the 2 hydrogens one face of the alkene, in this case the two methyl groups point the same way. That's these two methyl groups here. And the two ethyl groups point the same way as one another, but the opposite direction of the methyl groups. And now we see that we have a symmetric molecule. So we would get a meso compound in that case. So you can see it's very important to know that the two hydrogens add syn to one another, because that in turn will influence whether you get a racemic mixture or a meso compound as the major product of these types of reactions. The next type of reactions covered in the primer are reactions involving the electrophilic addition of a proton to an alkene as the first step of reaction. We have two general types of reactions. They differ only in what the nucleophile is following the formation of the carbocation by the electrophilic addition of the proton. The electrophilic piece of each of these structures would be an OH group that ends up on the product from a water, an OR group from an alcohol, or a halogen if it was hydrochloric, hydrobromic, or hydroiodic acid. In order to effectively solve this type of problem, we need to know what adds. We first add a proton in the electrophilic addition step, and then the nucleophile coordinates to that carbocation. How do the H and nucleophile add with respect to each other? It's actually going to be a mix of syn and anti-addition. Also, if there is a carbocation involved in a mechanism, as is the case here for all the reactions on this slide, you have to watch and see whether that carbocation might rearrange. The other thing that people generally talk about in terms of alkene reactions is whether the product is Markovnikov or non-Markovnikov. And this simply means that in a Markovnikov product, which we'll see here, you add the more electronegative atom to the more substituted side, the more substituted carbon of the carbon-carbon double bond. So let's consider this first example. If we do electrophilic addition, the pi bond will be gone. You will selectively add the proton to the less substituted side so that the carbocation here will be on the tertiary carbon, not down here at a secondary carbon. If it's already a tertiary carbocation, it's not going to rearrange. The nucleophile will simply do coordination, loss of the proton to that site, and you'll get your final product. Our second problem again begins with the electrophilic addition of a proton from the sulfuric acid to this double bond. Now, since this is a symmetric molecule and each side is a secondary site, it doesn't matter which site we choose for the carbocation. The second step is the coordination step, where in this case our nucleophilic piece comes from the methanol. This leads to our final product, which again is an achiral molecule. So we have our complete reaction drawn here with the major product. In the next case, we again have electrophilic addition of a proton to the alkene. In this case, we have a choice between a tertiary and a secondary site for the carbocation. The tertiary will be more stable and will be the more favored path. Once the tertiary carbocation is formed, we will have a simple coordination of the bromide to that site, leading to our product. In this case, we need to notice that there is a chiral center generated here from these achiral materials in the preceding step of the reaction. We need to draw all distinct isomers, so we should draw the R and S isomers of this product in order to get the correct answer. This will lead to a racemic mixture of these two distinct isomers. Next, we consider the same starting material reacting with either a hydrohalic acid, as we'd observe in a hydrohalogenation, or with sulfuric acid in the presence of water, as we would observe for a hydration reaction. In either case, our first step will be the electrophilic addition of a proton to one side of the alkene. That will leave the carbocation on the secondary site. So the H adds to this carbon that's less substituted, leaving the positive charge on the more substituted secondary site. In this case, we observe that the secondary site is directly adjacent to a tertiary site. Once the spontaneous carbocation rearrangement occurs to give you the tertiary carbocation, we should have coordination of the bromide nucleophile in the first case, or the OH part of water in the second case, after the water loses a proton. This will lead to these products. And these will be the major products of the reaction. Finally, for this set of lessons from the primer and the lecture guide, we have halogenation and halohydrin formation. You can differentiate these two reactions from one another because the halogenation features just a halogen such as bromine or chlorine. Sometimes a solvent will be shown, but the solvent will not be a nucleophilic one. We know that water can be used as a nucleophile, as we saw in the hydration reaction in the past couple slides. So if you have that nucleophile as your solvent and the bromine as the solvent, that gives you the conditions for a halohydrin formation. So it's first very important to be able to figure out which type of reaction is occurring, because the next thing we have to look for is to identify which atoms or atom groups add to each of the carbons in the carbon-carbon double bond. And when we consider how these reactions proceed, we add a halogen to each of the two carbons in the case of halogenation, and they add anti to one another. Whereas in the halohydrin formation, a halogen adds to only one of the two carbons, the OH from the water adds to the other side, and they do add anti to one another. One good clue for studying will be that when you see a halogen as a reactant with an alkene starting material, those are the only reactions we learn in the primer and lecture guide where the two groups that add to the carbon-carbon double bond add anti to one another. So with all of these pieces of knowledge in place, we can start off with our first example. With this cyclohexane ring with a methyl group on each of the two carbons of the double bond, we're going to have a bromine added to each of those two carbons, and they'll point in opposite directions of one another, anti to one another. So knowing that, we can quickly sketch in one of the products. We should recognize that this product is a chiral molecule, and you cannot make one specific chiral isomer from an achiral starting material. So we must have an equal amount of both enantiomers. When we have a 50-50 mixture of two enantiomers in this way, this is a racemic mixture. Let's look at our second example. We have chlorine as the halogen is going to add, and again they will add anti to one another. And again we get a chiral molecule. There's no symmetry, and we have two chiral centers in the molecule. We should get an equal mixture of both of these enantiomers, so again a racemic mixture is formed. Let's take a look at these bottom two examples, one a halogenation, one a halohydrin formation, where we have acyclic starting materials. Well, in the first case, we're going to have an anti-addition of the two chlorines, one up, one down. And remember, there are no rearrangements in the course of this reaction, so that if we have these two methyl groups point opposite ways to start, they're going to point in opposite directions in the product as well. Likewise with the ethyl groups that are positioned on this molecule. One will be pointed towards us and one away from us. Now, none of these groups are lined up, so it's difficult to tell whether this is a chiral molecule. We need to look for symmetry. In order to do that, we'll need to rotate this chlorine up to the top to see how the groups line up. Upon doing so, we see this molecule has symmetry and is therefore a meso compound. We would not draw a second distinct isomer because that would be incorrect. There are not two distinct isomers. There's only one possible major product. Next, we take a look at the only halohydrin formation that we have on this slide. And remember that if the two groups we add are not the same as one another, we have to consider to which side the OH adds and to which side the bromine adds. In this case, we have what is known as a Markovnikov addition. This means that the more electronegative atom will end up attached to the more substituted carbon. This is the more substituted carbon of the carbon-carbon double bond, and the OH is the more electronegative atom that's going to be bound. So we should get a structure like this. The OH has to be on the more substituted side. It has to be pointed the opposite direction, anti to the bromine. And we have two chiral centers. There's no possibility for symmetry because the bromine and oxygen are different from one another. But this is a chiral molecule. We should get a 50-50 mixture of this with the other enantiomer, and that would be a racemic mixture.